Well, now it's time to start talking about erosion. And I'm going to start off by making the statement that the number one agent of erosion anywhere water can exist is running water or streams. Now, that's anywhere water can exist, and note that also means in the desert, which we'll get around to. Well, first of all, let's talk a little bit about streams and some general statements about streams. There are two fundamentally different kinds of streams. The first kind of stream is what we call an exterior stream. And basically, that kind of stream system is one in which the water in the stream or any tributary to the stream eventually makes it to the ocean. That's what the exterior is all about. It gets outside the continent. On the other hand, the other type is the interior stream, in which the water heads up in some highland area, flows into some inland basin, and never makes it to the ocean. Now, when you think about all the streams of the world, by far, most of them are all exterior streams, and we'll get around to talking a little bit more about the difference between the two later. But I want to start off by talking about something called a hydrologic cycle. What the hydrologic cycle is a cartoon. And what this cartoon shows basically is that most of the water, well, everybody knows this anyway, is in the oceans. 97% of all the water on Earth is contained within the oceans. They cover 70% of the surface of Earth. And what happens out in the ocean, of course, the water evaporates, it's taken up into the atmosphere, the prevailing winds carried over land, and once it gets over land, it precipitates out. Now, precipitation can be in one of two forms, either rain or snow. Well, let's talk about the rain first. If it falls as rain, remember now, this is a cycle, so the object of the game is to get back to the ocean. Well, obviously, one way it can do that is simply flow off in the form of a stream. Now, along the way, it may rest for a while imponded in a pond or maybe in a lake, but they overflow and then complete the cycle back to the ocean. But nevertheless, streams are one way that water gets back to the ocean. The other way it can get back to the ocean is it can soak into the ground, flow underground back to the ocean, and we're going to have to explain how that can happen in another lecture, but that would be the other way that water can get back. Underground is groundwater. Now, let's talk about the stuff that falls as snow. If it's falling as snow in a climate like we live, in a temperate climate, of course it's a seasonal thing. The snows come and go after the winter's over. Then when they melt, they turn into water, and then it takes off either as a stream or underground again. But the one I want to talk about is the snow that falls and stays the year round over and over and keeps accumulating and turns into glacial ice. As soon as you use the term glacial ice, the implication is you're talking about ice masses now that are going to be around for a very, very long time. We're talking perhaps not hundreds perhaps, but millions of years. So it's locked up as ice. Now, that ice eventually will melt too. For example, as we speak, all the glaciers of the world are melting, are in retreat. So eventually, even glacial ice, regardless of how long it's been around, is going to melt, turn into water, which is going to go back to the ocean, either overland as streams or groundwater back to the ocean as underground. Now, here's a question I always ask my students. Thinking now about just the water outside the ocean basins. We're talking now about that 3% of what we refer to as fresh water. Where is it? Where do you think most of it is? Now, the choices are, note, streams, lakes, ponds, or whatever, glaciers, or underground. Now, and let me tell you how I picked it. When I was asked that question as a student, I thought about it for not too long, and I discounted glaciers right off the bat. The reason why I discounted glaciers right off the bat was I grew up in Pittsburgh, and we didn't have any glaciers in Pittsburgh. And of course, I knew there were glaciers out there. I'd read them in books, Antarctica and Greenland and all that. But I really didn't have any feeling how big those areas were. It just seemed to me they can't be that big compared to the entire continent of Asia, North America, South America. So I just discounted glaciers right off the bat. The next one I discounted were lakes. The reason why, growing up in Pittsburgh, of course, I knew Lake Erie. We'd gone up there as Boy Scouts, I guess. But in the immediate area where I live, there weren't any lakes that I could think of. And so I thought, well, if there are any around here, they've got to be few and far between. And so I just sort of, it can't be lakes either. So I discounted that one. But then I started thinking about groundwater. Because, for example, we had on our property a spring, which is groundwater. And we used to use the water to water the garden and things like that. Our neighbor had a really, really big spring. Matter of fact, they had a really, really big pond. They had fish in it and all kind of stuff like that. And then as I hiked around the hills around where I lived, I knew where there were a lot of springs. And so it just dawned on me, there seems to be an awful lot of water down there. Again, I didn't really have any feeling for how much it was, but I started thinking, well, maybe that's it. But then the thing that really dawned on me, every time I crossed the valley, across the ridge into another valley, there was a stream in that valley. And I soon realized that every valley had a stream in it. Now, it might not have water in it all the time, but every valley had a stream. And so I got to thinking, boy, there must be an awful lot of valleys in the world. And so that's why I picked streams. So it's very simple in my way of logical thinking that there probably is, that's where most of the fresh water is. Well, wrong. It turns out that all of the water in all of the streams and rivers of the world represents 0.0005% of all the water in the world outside the ocean basins. 0.005%. Almost insignificant. I think it is insignificant, but here's the point. That seemingly insignificant amount of water, given its time and thing, is what carves the land to make it look like it does. It is the #1 agent of erosion, which I think says something for the power that streams have. Although there's not much water involved worldwide, it's really going to do a job. So anyway, streams are the least. Now, of the remaining, where is it? Well, it really shocked me as a student to find out most of it is tied up in glacial ice. 80% of all the fresh water on Earth is tied up in glacial ice, meaning, though, that it's not available for us. 20% is in the ground. Now, note 20 and 80, that's already 100. That means we can forget about the others if you want to. Well, actually, lakes is about 0.7%. But here's the point I would like to make, and we'll take this up in another lecture, too, when we talk about groundwater. That groundwater, that 20% of groundwater, that's our source of water for the future. And I won't get on to talking yet about why we ought to conserve it. But there's where it is. So it's mostly in glacial ice, 80%. 20% of it is in groundwater. But note the tiny, tiny little bit is in streams. But that's still going to be the #1 agent of erosion. Now, the other things we had to sort of talk about to sort of set the scene. We're going to be talking about picking things up and carrying them away. That's what erosion is, picking things up and carrying them away. And we talk about various particle sizes. Well, we use names to describe various particles. These are names that you've used all your life, probably, cobbles and pebbles and things. But you see, the geologists, they mean a specific size. And the list starts off at the top to bottom: boulder, cobble, pebble, granule, sand, silt, and clay. Now, the important part about those is that there's no composition implied in any of it. No composition whatsoever. Somebody usually asks me about that clay one, the really, really small sizes down there. Why do we call it clay size? Well, the reason why is because what's in that clay size is almost entirely clay mineral. So I guess somebody figured, well, if that's what it's made up of, why don't we just call it clay size? But to give you some idea of what sizes are we're talking about, boulders would be anything greater than 10 inches, which would be what? About bigger than a volleyball. Cobbles would be from there down to maybe the size of a baseball. Pebbles would be there down to the size of a pea. Granules would be their size down to about a pinhead. Then we're talking about sand size now. Sand size would range from about a pinhead. Think of the stuff at the beach you can pick up. You can see it's about about pinhead size. Down to a speck of dust. Now we're getting pretty small. Now here's the significance of dust size. The biggest dust size particle, that's the limit of the human eye to see. Once you go below that, the human eye is not good enough to see anything smaller than that. So then the dividing line, of course, between silt size and clay size, I would just say it's microscopic. You'd have to have a really, really good microscope to see that, probably a scanning electron microscope. So that'll give you some idea of these particle sizes. Then the other thing we have to say a few things about, stream parameters. There are various kinds of measurements that we make on streams to be able to describe them. And one of them, some of these you probably already know anyway, but gradient. Gradient obviously is the slope of the stream channel, and it's measured in feet per mile. What we do is we measure out on a map 1 mile, figure out how many feet the stream has dropped. And the important thing, however, if you look at the profile of a stream channel from headwaters to mouth, it's not a straight line. It's a curvilinear line. In fact, as you go from the mouth to the headwaters, it increases exponentially, and that's the important part about the gradient. Now, volume. Well, it just means volume, but here's the point. A lot of people have it in mind that we're talking about the volume of the stream from headwater to the mouth. That's not how we measure the volume. The volume of the stream is measured at various points along the way, and the way we do it, we simply measure what we call the wetted width. That's simply the distance across the stream at the water surface. And then we take an average depth out and usually in the middle of the stream, and the product of those two is the volume. Note it's an area measurement, but it's the measure of the volume. Obviously, volume of the stream increases downstream because you have to take into account all the tributaries coming in and things like that. Here's an interesting one, velocity. Velocity obviously is just how fast the water is moving. But if you ask the average person, where along a stream do you think the water's moving the fastest? Invariably, a student will say, I think it's up in the headwaters. The reason why they're thinking now of these bashing, crashing mountain streams, you see, it looks like it's very, very fast moving. Well, I think that's sort of a question of perception oftentimes. For example, if you go up into your favorite crashing, bashing mountain stream, there will be a place where the water is indeed shooting right straight down the stream channel, downstream component of gravity, you see, and very, very fast. But note, for every one of those, the water will run into a rock and go that way, or maybe go up, or maybe that way. And there are places, those of you whitewater know, that it can actually boil back on you, going back upstream, you see. So when you sort of add all those things up together and take some kind of an average, it turns out that the downslope rate of movement of the water isn't quite as fast as you think it is. As a matter of fact, very, very detailed measurement of stream velocity has shown that there actually is a slight increase of velocity downstream. Not much, but a slight increase downstream. And when you think about it, it almost has to be that way. Because if it wasn't that way, it'd be like marching troops. If the troops in the front started slowing down and the ones in the back didn't know about that, they'd start climbing the ones backs in the front. And in the case of a stream, what that would mean would be the downstream somewhere between the headwaters and the mouth, the stream would go into a state of constant flood. And streams don't do that. The reason why is because nature saw to it that there is a slight increase in velocity downstream. Now, probably the most important of all these parameters is what we call discharge. Discharge is simply the product of volume and velocity. And the importance about discharge is that that's what determines the total amount of energy the stream has to do anything. Well, think about it. When would a stream have the greatest amount of discharge, volume and velocity, and therefore the greatest amount of energy? And it should pop into mind at time of flood. That's when the velocity and the volume is the highest. That's when the energy is the highest. Here's the point to be made, I think. The average stream on an average run-of-the-mill day really isn't doing much in the way of carving or sculpting the land. It's moving whatever water it has, granted. It's moving whatever it picked up somewhere, okay. But it really isn't doing any sculpting, the stuff we're going to try to talk about. When does all that take place? During floods. During floods. The average stream, well, the humid streams anyway, in humid areas, about every 2.1 years they go into a state of flood. So that's when the work is really done, is during floods. Now, the mechanism, how all this works. The hydraulic engineers have a thing called fluid flow. Now, fluid, remember, is any gas or liquid. We're talking here water, so let's talk water flow. They would visualize the flow of water in two ways, either laminar flow or turbulent flow. So picture, if you will, a stream, and picture, if you will, say molecules of water. In laminar flow, the picture is that those molecules of water would move downstream along absolutely parallel paths, not getting in each other's way, not crossing each other's paths, not interfering with each other. That would be laminar flow. Turbulent flow, on the other hand, if you picture those same molecules of water, they would be moving downstream, all right, everybody has to move downstream, but they're going in all kinds of directions, getting in each other's way, bumping into each other, and interfering with each other. Now, here's the deal. If I were asked to, say, just show me very simplistically how the energy is being expended in laminar and turbulent flow, here's what I would do. I would put an arrow, say in the case of laminar flow, just a horizontal arrow, and that represents the application of energy simply to move the water downstream. On the other hand, the turbulent flow, of course, there's going to be a horizontal arrow too, but then I would have another arrow pointed vertically upward, indicating that the water is being lifted. Now, we don't have to waste energy of the water bringing it back down because gravity does that. But that's the whole point now. In a turbulent system, you've got two components of energy. You've got a horizontal one and a vertical one. Okay, now let's just define erosion again very simply as picking and moving. You're going to pick things up and carry them away. Question: will laminar flow erode? I don't think so, because in order to pick things up and carry away, note to pick things up, you've got to get a force under it directed vertically upward. For example, I don't care if you're picking up a coffee cup or a stream picking a particle off the bottom. You got to get under it with a force directed upward first, then you can carry it away. Well, note there's no vertical component in laminar flow. So no, it won't pick up. Maybe somebody else picks up, it could carry, but it can't do the picking. So therefore, it does not erode. But note the turbulent flow, that's the secret of it. The turbulent flow has both components. It has the vertical component to do the picking, and then it has the horizontal component to do the moving. So that's the reason why it's the turbulence within streams that really does the job. It's the allocation of energy between those two forces. Now, let's just talk about streams again to sort of picture this in your mind. Picture a stream from headwaters down to the mouth. If you went to the headwaters, now we're talking about the typical bashing, crashing mountain stream. Very, very, very turbulent. Now here's how I would draw something very turbulent. I would have a very large vertical arrow and a very small horizontal arrow. It's a relative thing, you see. So that's how I would designate highly turbulent water. Well, note what that says. You got a great deal of energy being directed vertically upward, but not much energy being directed downstream. Why is it that way? All you have to do is to look in the stream bed and see. You got boulders and cobbles in there that weigh hundreds and hundreds of pounds. That's what this stream is expected to pick up during the flood and move downstream. Now, to pick it up, you need that great big vertical arrow. Now, what that little horizontal arrow means, you don't have to move it very far. Remember, we got all the time in the world, so a little bit at a time, you see, it's still going to move downstream. So it's that allocation of energy because that's what it has to do. Now, if we went further downstream, and if you are a fisherman or a backpacker, you walk downstream, and this is what you can see. The particles in the stream bed are getting smaller and smaller all the time. Why? Well, I mean, you still have weathering going on. You still have physical weathering that they're banging into each other, chipping each other off, you see. There's also chemical weathering still going on. I mean, the water still has oxygen in it and carbon dioxide in it. So the weathering is making the particles smaller and smaller. So the result is you don't need that great big vertical arrow much anymore. So the vertical arrow now is getting smaller, but note you got more stuff to carry. So the horizontal arrow is getting bigger. So note the relative magnitude now says the turbulence is dropping off. The reason why? It's the reallocation of energy to do the job you have to do. By the time you get down to the mouth of the stream, now what's on the bottom? Maybe sand-sized particles are very, very small now. You don't need an awful lot of vertical component to really pick that stuff up. But you've got a lot of stuff down there. So if you look at the mouth is where the turbulence is the least. So the reason why? Well, you don't need it. So you have a very small vertical arrow and a great big horizontal arrow. So this, I think, is a beautiful example of nature really reallocating energy to do the job it has to do. And so the next time you look at a stream, I hope you think about all that stuff. Now, I want to put all this stuff together to give you a little chart that I think really describes what the stream is doing and how it works. Now, here's what this chart is going to look like. I'm going to make a chart. On one side, I'm going to plot velocity of the water. And I'm going to make this very graphic. So when you look at the chart, you'll see that along the velocity side, increasing upward, I'm going to put a horizontal arrow, very small at the bottom, and increasing toward the top. And that's just my way of graphically saying the velocity is increasing along this side. Now, on the other side, I'm going to put that vertical component of turbulence, increasing in magnitude as you go up. Now, here's the reason why I can do that. In any stream segment, the relationship between the vertical and the horizontal arrow is sort of fixed, meaning that if you were to increase the horizontal arrow, the vertical arrow would increase along with it. So they sort of go hand in hand. So this is my way of saying, as you increase the velocity of the water, the vertical component is also increasing. In other words, the amount of turbulence, okay? Now, across the bottom, what I'm going to do is I'm going to put some of those particles we talked about. I'm going to put from pebble, granule, sand, silt, and clay. Now, we don't have to go above pebble because once we get there, you'll see how this all works. And then below each one of those, I'm going to put a down arrow. That down arrow, that's the force of gravity. That's the weight of the object, you see. So the bigger down arrow is under the pebble. The smallest down arrow is under the clay particle. Now, here's the way it's going to work. In order to pick any of these things up, remember, the up arrow has to be at least as big, if not bigger than the down arrow, before you can actually pick this thing off the bottom. So here's the way this diagram, as a matter of fact, is a result of a little research project that many people have done. And the way we do it, we have in the business what we call a flume. What it is, it's sort of an O-shaped racetrack that we drive water, an artificial stream. And one side of it is sort of like a big aquarium, so that we can look inside and see what's going on and make measurements and things like that. And so here we're going to do. We're going to put a pebble on the bottom. We're going to start increasing the velocity. When does the pebble start to move? Remember now, picking has to come first. You don't have to pick it all the way up, but you got to break contact with the bottom. Once it's picked, then you can move it. Now note, the down arrow under the pebble is pretty big. Pointing down, that's the weight. A very small up arrow isn't going to do it. So obviously what you have to do is increase the volume, increase the turbulence, until at least those two arrows are equal to each other. Now this is a critical balance. It says that if you were to exceed just a little bit, the vertical arrow just a little bit bigger, the thing would pick off the bottom and move. Now, if you do this experimentally, what you'll find out, it doesn't quite do it. What you have to do is you have to increase the velocity of the turbulence, not an awful lot more, but a measurable amount, and until the pebble starts to move. Now, what does it mean? You had to add more energy than really theoretically you needed to get the pebble to move. What was it you were overcoming? You had to be overcoming something. Well, I think one of the things is, if the pebble's sitting there on the bottom, you got to force water under it, first of all. So it's a physical thing. But my gut feeling is, it's got to have something to do with inertia. Remember, when at rest tends to keep things at rest. So anyway, once you exceed all that, then the particle comes off the bottom and starts moving. Well, okay, now let's granule. It's the same thing. You come up, there's a point where it should, there's a point where it does. All right, same thing with the sand. Now we're dropping off now, you see, because we're getting smaller, but there's a point where it should come off the bottom and a point where it does. So it's just the same. But now we come to silt and clay. The problem is, when the experiments show, you have to have the amount of energy equal to pick up a piece of silt. No, we're talking dust size now. As you had to pick up a granule, and you think that's bad, you've got to have the amount of energy, volume, velocity, and turbulence to pick up a clay particle as it does to pick up a pebble. Now, this can't be just forcing water underneath, and it can't be inertia and all that. There had to be something going on, and it took them a long time to figure this out. And here's what they finally came up with. It's a theory. The theory is that whatever the water comes in contact with the surface of the stream bottom, there is a layer called the laminar layer. This thing is probably only a fraction of a millimeter thick, and there is within this laminar layer pure laminar flow. Now, the idea is that the thickness of that laminar layer is a function of turbulence. As the turbulence increases, it thins down, thins down, thins down, and at some point would disappear. Okay, so note the clay and silt size. Even at silt size, at a dust particle, it's a lot smaller than a fraction of a millimeter. So the idea is that both those particles now reside totally within the laminar layer. There's no picking power. So what you have to do, you have to increase the velocity, increase the turbulence to get that layer thinned down to the point where the dust particles poke their head above that layer. The turbulence picks them up, snatches them away, and finally takes them away. But by that time, you see, you have the same amount of energy that it would take to pick up a granule. Now, the clay particle, microscopic, you have to eliminate that laminar layer, I suspect. And so you jack up the velocity and turbulence till it's gone, but by that time, you see, you've got the energy required for a pebble. And so finally, it comes off the bottom and moves. Now, if you look at the chart, we can connect up the upper dots. And you have a curve, and what this upper curve says, once you exceed this upper curve now, then the material will be picked up and carried away. Well, that's what erosion is all about. So that part of the little chart is labeled erosion. Note also, if I were to ask you, looking at a chart like that, What is the easiest particle size for a stream to pick up and carry? The average person would say, well, whatever the smallest particle is. No, it's sand size. Sand size is the easiest particle for a stream to pick up and carry. The smaller and the larger ones become increasingly more difficult for different reasons. But sand is the easiest particle size for it to pick up and move. Now, let's say we have this stream moving along and we've got enough velocity and turbulence to be picking all these off the bottom. Know what the bottom curve says. The bottom curve says you can drop the velocity and turbulence down until you reach that bottom curve. Remember now, that bottom curve is where the two forces, the gravity and the upward component of turbulence, are equal to each other. As long as you stay above that curve, they will continue to be carried along. Well, that's why that part of the chart is labeled transportation, because that's what it's all about. But once you drop below that lower curve, the particles will start settling back to the bottom. That's because the down arrow now is bigger than the up arrow. And note what it says. After it's all said and done, the big particles come down first, the little particles come down last. And if you've ever been involved in a flood, you know that. I mean, for example, you come back after a flood and your front yard, or maybe the house inside is covered with mud, the top is a sticky. Well, that's the clay size, you see, that came down last. But if you dig down through that stuff, you might get down and maybe sand at the bottom. So there would be an illustration of the relative the speed with they precipitate. Big things first, little things last. Okay, so that chart, I think, is wonderful. If you understand that chart, I think you can understand almost all the mechanisms and things and how the streams do their thing, because everything is sort of summarized in that one little chart. Now, there are two other words I want to talk about, though. One is capacity and one is load. Now, these are two words that are often confused by students, and they think they're the same, but they're not. By definition, capacity now is the total amount of material the stream can carry. That's a can. Load is the total amount of stuff that the stream is carrying. Now, there's a big difference between can and is. For example, they say that if you're in relatively good shape, you ought to be able to pick up your body weight and carry it away. I may have been able to do that at one time. Probably when I was in basic training, I could do that. But I'm not going to try that now. But anyway, that's your capacity, your body weight. Question, on an average run-of-the-mill day, are you carrying your body weight? No, of course not. What you're carrying, the weight of the clothes on your back, your shoes, maybe a little bit of jewelry, that's about it. But note what it says. Your load is far less than your capacity. Big deal? Well, you can always carry more. I'm thinking of the students now carrying that big book bag. That's the heaviest thing they carry. If you're walking down the street and somebody says, hey, could you help me carry this? Sure, I can carry that. Why? Because you're nowhere near your capacity. That's the way streams are. For most of the life of the stream, they're operating where you have the capacity greater than the load. They can always carry more. Now, one last thing about load. The load comes under three different categories, the way it carries load. Dissolved load, suspended load, and bed load. Now, dissolved load, of course, it just says what it is. It's stuff that's in solution. What is it? Well, before you and I showed up on the scene, what it was all those soluble bicarbonates that went into solution as a result of chemical weathering, a little bit of silicic acid. Now, of course, since we came onto the scene, there are other things that I don't even want to think about in solution. Suspended load. The suspended load is largely those fine materials, the clay and the silt being carried up in the water. That's what makes a muddy water. That's the difference between a bashing, crashing mountain stream that's crystal clear, it has none, as opposed to a major stream where you can't even see the bottom. That's the suspended material, the silt and the clay. The bed load now is the stuff that's being carried along the bottom. Probably the smallest size is sand size. This is not quite able to be up into the water and become part of the suspended load, but it can be moved along in the bottom. And then there's going to be some upper limit, some limit as to which it cannot exceed. That's called the competency of the stream. Now, that's going to change from day to day. For example, on a run-of-the-mill day, the competency of a stream could be pebble size, let's say. But put this stream in flood, this same stream could have the competency of a boulder, or your car, or a bridge. You see, there's no upper limit, really. It just depends on how much energy. So anyway, of those three, which one is the most important? Well, that's hard to say. For example, if you're up in the headwaters of a stream, if you think about your crashing, bashing mountain stream, perfectly clear, no suspended material, it's perfectly clear, that's why. Dissolve load, probably very, very, very small dissolve load. Why? There's not enough of rock influenced in the area to provide those dissolved stuff. So most of it's bed load. That's what you can see. All those great big boulders under your feet there, that's the bed load. But now by the time you get down to the mouth, things have changed. The bed load has dropped off in abundance, the suspended load has increased, and so has the dissolved load. Now, just to give you a comparison, I looked up some data for the Mississippi. And this would probably be comparable to any of the major streams of the world. This is amazing. I was sort of surprised when I saw this my first time. The dissolved load, the Mississippi River, the dissolved load represents 25% of all the stuff the stream is carrying. Now, that's a lot of stuff when you think 25%. The suspended load, 68% is in suspended load. Now note, that's where most of them are, and I think that probably is true for most major streams. The suspended load is always the biggest of the bunch. Bed load, well, you can do your own subtraction yourself. So the idea is that by the time major streams get to the ocean, most of what they're carrying is the suspended load, the fine materials. Remember the clay minerals, and then the next one would be all those dissolved ingredients were being hauled off, and then the bed load would be the least important of all. Well, we're going to go on and continue our discussion of streams and talk about sculpting of the land next.